Okay, perfect. So we'll start the presentation.
And today I'm going to talk.
Can you please also make sure that you can actually hear the video?
Yeah, we hear it.
Okay, perfect. Let's start then.
For assessing privacy risk in a health records lab using real-life data about the COVID virus in Denmark. The framework should serve as an analytical tool for data controllers to take informed decisions regarding privacy risk when collecting and disclosing data. More specifically, I will demonstrate the effect of attacker knowledge on different types of privacy risk and different types of anonymisation of data. The framework is based on the Privug method, which uses probabilistic programming to quantify risk analysis in data analytics. My name is Siv L Steffensen, and this is joint work with Louise Halvorsen, Willard Rafnsson, Oksana Kulyk, and Raúl Pardo. And first I'll talk about our motivation of the project, then the scope, and about attacker knowledge, the conceptual framework, and the Privug method, and anonymisation programs, then our disclosed queries, and at the end I will talk a little about our results. So we started this project right in the beginning of the outbreak of the COVID-19 pandemic. This was before anyone knew the exact scope of the crisis. At this point, the primary focus was to reduce the spread of the virus, and not many people considering the risk of disclosing a lot of data about the virus and the infected. Therefore, we found it interesting to investigate particularly the privacy risks of releasing this type of data about COVID-19. It's an important field because privacy concerns of individuals has become more and more relevant in regards to the big amount of data and data collections that are being disclosed and are becoming public available. All this available data may lead to privacy risks for the individuals represented in the datasets. The data controllers are then faced with the challenge we call attacker knowledge. This data, attackers may have a lot of other information than the disclosed data from, for example, public media, so-called domain knowledge, and so on. This data matched with the disclosed data can make the attackers able to identify records in the disclosed data if it's not properly anonymized. The problem of insufficient anonymisation is very broad, and we were very much inspired by a study conducted by Sweden, who was able to uniquely identify 87% of the US population by date of birth, sex, and SIP. What she did was just simply joining her medical data with voter lists, and then looking at the combination of the common demographics. Said in another way, consider the anonymisation of medical records. Here, the input data has 5 columns: name, zip code, birthday, sex, and diagnosis. The anonymisation is the algorithm called here, which simply removes the name column. If the attacker already possessed a dataset with zip code, birthday, and crucial name, then by simply joining the attacker can reveal the names in the medical record. This is a linking attack. Another example is the homogeneity attack. Here, birthdays are replaced with age group as anonymisation. The attacker, though, knows that Alice is in the records, being a middle-aged woman in zip code 2300. Here, all records making these constraints are new. Therefore, the attacker can learn that Alice is still in the figure. But what is the attacker knowledge in our framework? So in our approach, we consider 2 types of attacker knowledge: a uniform prior and a COVID prior. So with the uniform prior, the attacker knows nothing about the Danish population and the COVID-19 infection rates. This prior consists of attributes that are mostly uniformly distributed. Opposite, we have the code prior. Here, the attacker is informed about public statistics available to us of the first few months of the corona outbreak in Denmark. The attacker knows the distribution of age and sex for the Danish citizens. And here you see the distribution for the COVID prior. This is real-life age distribution in Denmark and the COVID-19 distribution here on the right side. Now, so a little bit about the framework. We have some attacker characteristics. Then we present 3 dimensions, 3 disclosure risks represented by queries, and I will briefly talk about the Privug data. So first, we consider an attacker that has some prior knowledge about the input data set. This is the uniform prior or the code prior. The attacker knows the program we will look at, and the attacker observes the output of the program. The goal is here to infer additional information about the input data set. So yeah. And then the framework introduces 3 dimensions to consider in a privacy data analysis. It's the distinctness, informedness, and granularity. The distinctness, as the slide says, is the quality of the input data representing the extent of which records in the input data are uniquely identifiable. A record might be similar to many records in the input data set, but it could also be unique or somewhere in between or have outliers. Then we have the informedness dimension, which is the quality of the attacker representing the extent of which the attacker is informed about the input. Analyzing with varying degrees of informedness enables data controllers to assess how attacker knowledge affects privacy risks. And at last, we have the granularity, which is the quality of the disclosure program representing the extent of which data has been distorted or reduced during disclosure. In our case, we test 2 different anonymisation programs. Another thing in our framework is our 3 disclosure risks represented by queries. We have the identity disclosure. Here we simply ask, can the attacker identify the precise record belonging to a data subject? And this will be the most severe disclosure if you could identify a specific record. Then we have the attribute disclosure. Here we ask, can the attacker learn the value of the attribute of a data subject? This is somewhat severe disclosure where you just learn some more data from just one single attribute. And then the quantitative attribute disclosure. Here we ask, can the attacker change their beliefs or certainty about the value of an attribute of a data subject? So to reason about privacy risks stemming from the use of an anonymisation algorithm, we use Privug developed by Pardo, Rafnsson, Cross, and Associates. I will briefly take the concept. In Privug, we define the attacker knowledge as a probabilistic model. If you look at the figure, you can see the steps of Privug divided into 2 phases, the modeling phase and the analysis phase. In the modeling phase, we first define the attacker knowledge about the input of the program before observing the output. This is our 2 different priors. These are modeled as a distribution over input data sets. Then there is the disclosure program, which we define the probabilistic version of the anonymisation program. Here we use 2 different anonymisation programs. And the last thing in the modeling phase is the observation. It is when we condition on the program's outputs. This is especially required for the quantitative attribute curves. And then we have the analysis phase. There are 2 steps. There was 0 posterior, where the knowledge of the attacker after observing the output is computed. Here, Privug uses importance sampling to estimate the posterior by repeatedly generating data sets according to the prior and run the disclosure programs on each of the samples to estimate the distribution of output data sets. And at last, we have the posterior analysis. Here, the private method is to query the prior so the data controller can analyze what the attacker learns about the input from the output. So we are using two anonymisation programs. One which will remove an attribute. In our case, it drops the name column in our data sets generated. And then we have attribute generalization, where we decrease the granularity of attributes by making, for example, the age attribute into intervals and then grouping. So this is the example. I will show you some examples of queries. And here the attribute column for age in the record is denoted as A, where the victim's age is denoted as capital H. So for the identity disclosure, this is an example of query. This will return the probability distribution of how likely it is that different numbers of records will contain the same age as the victim. And then we have the attribute disclosure. It is simply asking what is the probability that for every record that is generated in the dataset, there exists exactly one record with the victim's age, and then that person is ill. And the last one is the query for the quantitative attribute disclosure. Here we are looking for the probability distribution of the record having the same age as the victim and being ill, given that there is K records with the victim's age. So we condition with a number K. And now to the results. So here we have the results for identity disclosure. We see on the left side these violent plots should be read vertically as distribution histograms. So by looking at the mode for the elderly people, we see that it is much lower for the informed COVID prior than for the uninformed uniformed prior. Seen in the COVID prior, the highest risk is seen at the age of 90 with only the name removal as anonymisation program. Here there is a risk of 50% probability of being identified. So, but in this age group, the uniform data then leads to an underestimation of risk in a real life scenario. Though it is onset for the younger groups, where the uniform prior constitutes a worst case analysis for identity disclosure. When we generalize the ages, the risk of being identified naturally decreases for both priors. For under the age of 80, the mode increases with a factor 20, and above 80 with a factor 30. So increasing granularity notably decreases the identity disclosure. So, and this is the result for the attribute disclosure risk. These, here we observe the same effect of distinctness as in the identity disclosure analysis. When we compare the plot in the top, which is the uniform prior, with the plot in the bottom, which is the COVID-19 prior, we see that the values for the probability of learning the diagnosis are lower in the COVID plot. Ages from 0 to 79 is at higher risk in the uniform prior than in the COVID prior. Though for age groups above 80, the opposite holds. Again, the uniform prior underestimate the risk in these age groups. Furthermore, the attribute generalization is not sufficient in age groups above 80. Age groups between 0 and 79 are not low either, but better anonymized with more attributes being generalized. And at last, we have results for the disclosed quantitative attribute disclosure. We look here at how certain the attack is that the victim is ill, conditioned of a number of rows sharing the victim's age. So we operate here with two different types of records. One where the victim's age is 32, which we call ordinary, and one where it is 90, which we call outlier. So for the ordinary age facts, certainty decreases from 33% in the uniform prior to 17% in the COVID prior. However, for the COVID prior, the attacker learns proportionally more than for the uniform prior. So this is important to note because in some cases, the data controllers cares about the attacker's prediction of the victim's illness, whereas in other cases, the data controller may care about how much information an attacker could learn. And the takeaways for this is that with these results, we hope that data controllers will make better informed decisions on collecting and disclosing data, or will be able to inform people in different age groups about the risk of disclosing their data and seek their consent maybe even before actual data is collected. Because like we saw in our results that age group 90 for the COVID data is much more vulnerable. So it needs more consideration if you want to collect COVID-19 data about those age groups. Also because there are fewer people, the distribution of the ages in Denmark, there are fewer people that are old, and there were fewer people, like especially in the data we had, like in the beginning of Corona, that was infected with the coronavirus. So if one elderly person was infected, then it was also very much easier to identify. But then, yeah. But thank you for listening.
So let's stop sharing. Unfortunately, the presenter is not with us today. So if you have any questions, I would suggest to email the correspondent author of this proceedings. But we'll move on. One of the authors is here with us today online.
So I'm one of the authors.
Yeah, Willard.
So I can accept questions if there are any.
Okay, perfect.
First, let me say thank you so much for accommodating this. This happened on very short notice that our speaker was unable to attend, and we're very grateful that you could play back the video for us.
So we'll be able to finally get some questions. If you let's start with in-person questions. If you have any questions for Mr. Willard.
Quick question. In the analysis you did, were there any attributes which you found could be more useful to the attacker than some others? Like, was that any insight related to that?
Yes. So this was one aspect of our analysis. We looked at which attributes in isolation were useful to the attacker and which attribute combinations. So quasi identifiers essentially. We found that the zip code was quite useful. I mean, no attribute on its own was useful to the attacker, except in the case where we were doing the analysis for an outlier. If we're doing the analysis for an outlier, there are very few very old people. So if the attacker happens to know that the victim is in the data set and the victim is very old, then it would be quite easy for the attacker to find that record, even if the name has even if the name and other identifying information has been wiped from it. So in our quasi identifier analysis, where the attackers try to pinpoint which record belongs to the victim, it was it was sufficient to use, for instance, the age and zip code, or the age and birthday. Those two were a pseudo identifier which can identify well, in many cases, an individual. And we think that here the zip code was the thing that contributed most.
Thanks a lot for that. Appreciate it.
Hi, so I'm here from the room. Very nice, very interesting presentation. So my question was like, now that we have like a way to basically guess the quasi identifiers that can be used by the attackers, do you think we can also do you think your algorithm can also detect the level of anonymity we need in this quasi identifiers to basically hide this information and prevent such attacks?
Yeah, so because the analysis is because the analysis identifies quasi-identifiers, the analysis is capable of essentially reporting back to the data controller which attribute combinations they should not disclose in the plane, and that if they need to disclose those attributes, they must do sufficient generalization or obfuscation of those attributes. So this is the tool that is that we demonstrate this approach with, which is currently called Privug. It's implemented in Python, and you can Google it and find it. It supports this kind of interactive style where the data controller runs the analysis, learns something, and then makes changes to, for instance, the anonymization algorithm, and then runs the analysis again. In this case, for instance, the data controller would figure out that disclosing zip code and birthday together is bad, and that the data controller needs to not do that or obfuscate those attributes. So then the data controller could, for instance, do either, and then rerun the analysis and see what that does to privacy guarantees.
Right. So just quick follow up. Like it can so your the system can like identify the the identifiers that you need to hide, but can it also like say, like for example, do we really need to hide the entire zip code, or can we like maybe release like the first 2 digits, and basically can we detect that the level of anonymization we need there?
So yes to both questions. Yes to both proposals, I suppose. So there's it depends on the data, or rather what we assume about the data. So for some kinds of so suppose you have a concrete data set of individuals or records on individuals. For some such data sets, it would be fine to just disclose the first 2 digits. For other such sets, it would not be. For instance, if everybody's from maybe if everybody's from the same area in the United States, or if you have picked sort of uniformly picked people from across the United States, you get different guarantees if you use one specific way to generalize the zip code. So the key thing here is that our approach enables the data controller to try out different generalization approaches, and then pick one that fits best for their scenario. And this is something that is not something we normally see in existing tools. They even assume one specific scenario. Yeah, well, that's basically what they do.
Thank you.